I'd like to walk you through a little bit more of a structured approach of arriving at z-test as we did in the last video. And part of my reasoning behind that is in this video, you're also going to learn an additional tool to use in the calculator. And so as we start to use all kinds of different stat tools in the calculator, we really need to be a little bit organized, and we need to have an idea of when it's appropriate to select a particular tool. And so recall that the theme in Module 7 was all about means and proportions. The theme in Module 8, again, about means and proportions. And in this module, once again, our focus is means and proportions. And, you know, with confidence intervals, we were always interested in estimating a mean or estimating a proportion. But with hypothesis testing, it's all about checking the plausibility of a specific mean, or eventually you'll see also checking the plausibility of a specific proportion. And so in the last video, we saw that we would create some hypotheses. I don't know if I emphasized enough that the sample size in our problems needed to be at least 30, or our original population needed to be approximately normal. And then if sigma, the population standard deviation, is given, then our test statistic, which arrived as part of a standardization process, was a z-score, and z-score was perfectly normally distributed, and therefore we sometimes call that normal distribution a z-distribution, and the test that we used in the calculator was z-test. And our conclusion from the hypothesis test was related to the p-value. If our p-value was greater than our significance level alpha, then we failed to reject the null hypothesis, and we said it was inconclusive. There was just not enough evidence to accept the alternate idea. Whereas if the p-value was smaller than that significance level alpha, we would reject the null and accept the alternate or the researcher's hypothesis. So in this video, it's very similar. We're still going to be checking the plausibility of a specific mean. We still have to make sure that n is greater than 30 or our original population is approximately normal, but this time sigma is not going to be given. And when sigma is not given, that means S, the sample standard deviation, is going to be given somehow. And as you might remember going back to Module 8, when we use S in place of sigma, it introduces some variability into our test statistic. And so our test statistic in the standardization process no longer follows a z-distribution or no longer follows a normal distribution. Instead, it follows a t-distribution. And since you're working with a t-distribution in this context, we are using t-test in the calculator. The nice thing is the conclusions that we make are the exact same. They're all based upon the p-value. If the p-value is greater than alpha, then we fail to reject the null. And if you fail to reject the null hypothesis, you just say there's not enough evidence to reject the null, there's not enough evidence to accept the alternate. Whereas if p is less than alpha, then we can reject the null hypothesis and arrive at our researching idea. Okay, so refer back to this as you're completing this, some of the examples throughout this module. And we'll come back to filling this portion of the decision tree out in the very next video. But right now, let's go take a look at a couple of examples where we are doing hypothesis testing for a population mean and sigma is not known. So here's example 1. In a recent medical study, 76 subjects were placed on a low-fat diet. After 12 months, their sample mean weight loss was 2.2 kilograms. With a sample standard deviation of S equals 6.1. Can we conclude that the mean weight loss is greater than 0? Use the alpha equals 0.05 level of significance. So the first thing that you should note is we're doing a hypothesis test. So if you have that decision tree out, you're saying, is this hypothesis test involving means or proportions? And you would take a look at this and you'd say, oh, well, I'm doing a test involving means. And then the other thing that you really need to be considering in the beginning of this is your sample size sufficiently large, or is your original population approximately normal? We have 76 subjects, and so our sample size is sufficiently large. So I suggest at this point writing our hypotheses down. And you can see our main question of interest is, can we conclude that the mean weight loss is greater than 0? And that essentially captures the researching hypothesis, which is our alternate hypothesis. And so let's note here that our alternate is that the mean is greater than 0. And therefore the null would mean no change in the average weight loss, or the average weight loss would be equal to 0. So we've got our hypotheses. We know that this is a test involving means. We also know that we're given a sample standard deviation and we met the sample size condition. So we're being directed to use the t-test tool in the calculator. So we press stat, we go over to tests, and t-test is number 2. Make sure that you have stats selected because they've given us the summary stats and have not given us the data. Let's enter the null value of the mean, which is equal to 0. So I've got 0 there, so that's good. Now let's scroll down, and next to X bar, let's enter the sample mean. We can see our sample mean is 2.2. It's nice here that they ask us for S. That's exactly what we're given right here. S is 6.1. And our sample size, we need to enter that, is 76. Also, select the correct alternate hypothesis, and we want the average weight loss to be greater than 0. So I'm going to scroll over, select that one, and then I can calculate. And when I calculate, it's going to produce a p-value. And you can see here that the p-value is 0.0011936. And typically you're rounding to 4 decimal places, so that would be 0.0012. And we can observe that 0.0012 is lower than our cutoff of 0.05. And when our p-value is lower than the alpha cutoff, as you saw in the decision tree, we can reject the null. And in this case, if you're rejecting the null, then you're saying that the average weight loss appears to be greater than 0. Okay, let's take a look at example 2 now. Example 2 says, generic drugs are lower cost substitutes for brand name drugs. Before a generic can be sold in the U.S., it must be tested and found to perform equivalently to the brand name product. The U.S. FDA is now supervising the testing of a new generic antifungal ointment. The brand name ointment is known to deliver a mean of 3.5 micrograms of active ingredient to each square centimeter of skin. As part of testing, 7 subjects apply the ointment. 6 hours later, the amount of drug that has been absorbed into the skin is measured. The amounts in micrograms are given right here from those 7 subjects. How strong is the evidence that the mean amount absorbed differs from 3.5 micrograms? Use the alpha equals 0.01 level of significance. Okay, so we've got a few things happening here that we need to talk about. First off, here's your clue that this is a hypothesis test. And we also know that this involves means. Okay, we should note our hypotheses right away. And a lot of times, your alternate hypothesis is going to be captured in this question that they ask. So when it says, how strong is the evidence that the mean amount differs from 3.5 micrograms, your alternate is going to be the mean differs from 3.5, is not equal to 3.5. Whereas the null is that there would be no change in the average amount of medicine that this generic is delivering, and so therefore we would expect the average amount of medicine that the generic is delivering to be equal to 3.5. Okay, so the only other thing from the decision tree that you really need to be thinking of right now is the sample size requirement. And you'll notice that the sample size is not at least 30 here. There's only an n of 7. And so what that means is we need to know that the population from which this sample is drawn is approximately normal in order to proceed on that decision tree, in order to assume that our distribution of sample means is approximately normal. And so this is where it's helpful to use some of those tools that we've already learned in this class, such as dot plots or box plots or stem and leaf plots or normal quantile plots. And what you can do is you can enter this data into the calculator by saying stat edit. You can see I've entered my data into L1, and we can select one of those tools from the stat plot menu. The one that I have selected here, turn the stat plot on, the one that I've selected is the normal quantile plot. And if I press zoom number 9, it takes me to my normal quantile plot. And even though there's a little bit of a blip in here where it's not perfectly linear, I would still consider this to be approximately linear. And you might remember, when a normal quantile plot is approximately linear, we can conclude that this sample is coming from an approximately normal population. Okay, so with all that said, you should also note that we aren't given summary statistics here. We're just given the data itself. And when you're given the data itself, then that means you're definitely not told what a population standard deviation is. The only standard deviation that you can get from data is S. Now, we don't know what S is here. The calculator is going to be able to calculate that for us. But the nice thing is, when we go into TTEST, which is the tool that we're using again because we are not given sigma, the true population standard deviation, when we go into TTEST, we will notice that we can select data. And as long as you have entered your data in list 1, where this says list L1, then you're going to be fine to proceed this way. Now, if you put your data into L2, just make sure that your list here says L2, or if you put your data into another list, just make sure that this list that you have labeled here actually reflects where your data is. This should be the null value of our mean, and we can see that the null value of the mean, scroll down here, is equal to 3.5. Change that to 3.5. There we go. And then my frequency, I'm always going to leave that on 1. And I do have to change the alternate hypothesis here to be a differs symbol. And now I can go down and press calculate. And when I press calculate, I'm again going to get a p-value from a t-distribution. And my p-value here is 0.0255819. And again, typically, if we're going to 4 decimal places like we often are in Connect, then this p-value is 0.0256. And note, 0.0256 is actually greater than our alpha cutoff of 0.01. And so this is where we would say we fail to reject the null. And if we fail to reject the null hypothesis, then it is inconclusive. It is inconclusive whether or not the mean amount absorbed from this generic that we were testing differs from 3.5 micrograms. And so we don't have enough data, or our data are not convincing enough for us to say that this generic is going to differ from the mean of the brand name. Okay, so again, use the decision trees to help you decide what tool you're going to be using. And in the next video, look for an explanation of using that decision tree for a problem involving proportions.